Hey everybody, this is our video solution of problem 2 from Quiz 13, Spring 2023, Math 302 at Cal State Fullerton. In this problem, we are given a ring R, which is a PID, so a principal ideal domain, and we have an element X in R, which is indecomposable. So recall, X being indecomposable tells us that if we could ever factor X as a product of elements in the ring, one of the factors has to be a unit. And so we want to prove that the quotient ring is a field where, by the quotient ring, I'm referring to modding out by the ideal generated by X. So in order to show that a quotient ring is going to be a field, it's enough to show that the ideal is maximal. So to show R modulo the ideal generated by X is a field, it suffices to show the equivalent condition that the ideal generated by X, that's the ideal we're modding out by, is a maximal ideal of R. Okay, so this is one of our important results from class. It's actually equivalent. If you mod out by a maximal ideal, you get a field. If when you mod out by an ideal, you get a field, you must have modded out by a maximal ideal. All right, so what do we need to do to show that this ideal is a maximal ideal? Well, let's assume that I is an ideal of R such that, I'll just say contains, I contains the ideal generated by X, and of course it's contained, I is contained in R. Okay, in order to show that this ideal generated by X is maximal as an ideal, we need to show that this I we found is just equal to the ideal generated by X or is equal to R. Okay, now we know though that R is a PID. Okay, and that's very important here because it means that this I, this random ideal we found, actually has a generator. So since R is a PID, there exists some, how about Y in I, such that I is generated by Y. Okay, but now that tells us that the ideal generated by X is contained in the ideal generated by Y, which tells me that the element X, which we know is an element of the ideal generated by X, because we're working in a PID, so there's an identity element in R, we know that X is also an element of the ideal generated by Y. And therefore, this implies that there exists some, I don't know, how about we'll just call it R in R, such that X is equal to Y times R. All right, but we have just found a factorization of X in the ring R. So since X is indecomposable, then we know one of the factors has to be a unit. So Y or R is a unit of R. Okay, so there's two cases. So if Y is a unit of R, well, now we have an ideal I, right, generated by a unit. Oh, well, we know that if you put a unit into an ideal, then the ideal becomes the entire ring. So if Y is a unit, then I, which is equal to the ideal generated by Y, is equal to R. Okay, well, what if R is the unit? So if little r is the unit, well then of course little r has an inverse. So then R inverse is an element of R. And, well, what did I have here? X was equal to Y times R, but if I multiply both sides of that equality by R inverse, well, on the right-hand side, the R will go away, and so I'll just end up with XR inverse is equal to Y. But this tells me that I can write Y as a multiple of X, i.e. that Y is an element of the ideal generated by X. But if y is in the ideal generated by x, then the entire ideal generated by y must be contained in the ideal generated by x. Because again, ideals are closed, right, under R multiplication, right? They absorb R multiplication. So any multiple of y is also going to be in the ideal generated by x. But we already knew that the ideal generated by x was contained in the ideal generated by y. That was our assumption from the beginning. And therefore, the ideal generated by x is equal to the ideal generated by y, and that's of course equal to I. Okay, and so we've concluded that either I is equal to the entire ring or just equal to the ideal generated by x. Therefore, the ideal generated by x is maximal, and therefore R modulo the ideal generated by x is a field. And there we go. We'll see you next time, everybody.